Imagine for a second, you are cruising down the highway.
All right.
You're doing like 80 miles per hour in a state-of-the-art electric vehicle. And, the AC is blowing, the ride is super smooth, it's completely silent. But inside the sealed high-voltage heart of the car's traction motor, the laws of physics are basically staging a revolt.
Oh, yeah, a violent one.
Right. In just a fraction of a second, the microscopic electrical insulation wrapping the motor's copper coils begins to fail. I mean, its molecular structure is literally breaking down.
Yeah.
So what happens next? Like, how does the vehicle's onboard architecture recognize this totally invisible threat and prevent a catastrophic high-voltage failure? Because we're talking about a literal fire or lethal arcing to the chassis in literally the blink of an eye.
Well, when we say the blink of an eye, we're actually being generous. Yeah. In the automotive safety world, particularly when we're dealing with what's called an A04 classification, which is the industry's absolute highest risk level for hardware and software systems, the architecture has what is called a fault-tolerant time interval, or FTTI.
Okay, an FTTI.
Exactly. And for an insulation failure at speed, that interval is precisely 60 milliseconds.
Wow.
Yeah. The system has 60 thousandths of a second to sense the degradation, run the diagnostics, calculate a fallback strategy, and then mechanically execute a response that saves the vehicle and the occupants.
60 milliseconds to prevent an explosion at 80 miles per hour. That timeline is just wild to me.
It's incredibly fast.
It really is. So today's deep dive is a technical mission into that exact 60 millisecond window and the immense engineering required to actually survive it. We have this highly technical engineering dossier today, and it's basically a blueprint for survival inside an EV's dual motor controller system.
It really is a blueprint, yeah.
So we are going to dissect the architecture of EV motor insulation from basically every angle. We're starting at the subatomic level with the physical root causes of the degradation, moving through the vehicle's lightning-fast diagnostic software, looking at the structural countermeasures in the design FMEA, the extreme precision of the manufacturing floor in the process FMEA, and finally, the brutal hardware validation tests these systems have to survive.
It's an incredible journey because what you're really looking at here isn't just, car parts. It is a relentless battle against fundamental physics, electromagnetism, and chemistry.
Right.
The engineering required to contain 800-volt architectures while also optimizing for efficiency, it just pushes current material science to its absolute limits.
Okay, let's unpack this, because before we can fully appreciate how the system saves itself, we really need to understand the threat vector. What is actually attacking the motor's internal insulation? Because when you look at the root cause analysis, the primary instigator is something the EV industry usually champions as, like, the holy grail of efficiency.
Right, the silicon carbide inverters.
Yeah, the Sigerty inverters. Why does our source material paint them as the villain here?
Well, what's fascinating here is the sheer engineering paradox of high-performance components. Silicon carbide, or silicon inverters, are revolutionary because they switch voltages incredibly fast, which minimizes energy loss.
Okay.
But that extreme switching speed creates an electromagnetic nightmare downstream, specifically a phenomenon known as high-frequency DVDT.
DVT.
Yeah, just the change in voltage over the change in time. With Sigerty architectures, we're looking at violent voltage rise rates, frequently exceeding 10 kilovolts per microsecond.
10,000 volts in a single microsecond. To a non-engineer, I mean, that just sounds like a big number, but dynamically, what does that actually do to a wire?
It creates severe wave reflections. Think of the electrical pulse leaving the inverter like a heavy battle rope tied to a concrete wall.
Okay, yeah.
When you whip that rope, a wave travels down its length. When the wave hits the rigid wall, which in this case is the impedance mismatch at the motor terminals, it doesn't just stop.
Right, it snaps back.
Exactly. The reflecting wave collides with the next incoming wave from the inverter.
Ah, so they stack on top of each other.
Precisely. You get localized voltage doubling.
Yeah.
And the first few turns of the copper coil inside the motor absorb almost all of that massive, disproportionate electrical stress.
Wow.
Yeah, the voltage spikes so high and so fast that it actually exceeds the dielectric breakdown strength of the microscopic air pockets trapped in and around the insulation.
Wait, the air itself fails? Like it just stops acting like empty space and becomes conductive?
It ionizes.
Oh, wow.
Yeah, when the electric field concentrates to that extreme degree, it strips electrons from the gas molecules in the air. This triggers a localized microscale electrical storm called partial discharge, or the corona effect.
The corona effect.
Right. You have these invisible, high-energy electron avalanches constantly bombarding the polymer chains of the wire enamel. And furthermore, That ionization splits oxygen molecules, creating ozone.
Oh, and ozone is an incredibly aggressive oxidizer, right?
Extremely. It chemically attacks the resin. It literally eats the insulation alive, carbonizing it molecule by molecule.
So it's not like a massive lightning bolt short-circuiting the car all at once. It's this parasitic, microscopic storm just slowly rotting the walls down.
Exactly.
But that's just the electromagnetic attack. You also have the thermal reality of high-performance driving.
Right, heat is the great accelerator here, governed by Arrhenius thermal aging.
Right, the Arrhenius equation.
Yeah, we all know heat degrades polymers, but the Arrhenius equation dictates that this isn't a linear decline. The relationship is exponential. These traction motors are operating between 130 and 150 degrees Celsius under extreme loads.
Okay, let's unpack this with an analogy. It's kind of like baking a rubber band, right? The heat oxidizes the material, it loses its elasticity, gets brittle, and its dielectric strength just plummets.
That's a perfect way to look at it. And if an engineer pushes that thermal threshold even just a few degrees higher for extra performance, the chemical bonds in the insulation don't just degrade slightly faster.
They break down exponentially.
Exactly.
Yep.
At an exponentially accelerated rate, the dielectric strength drops off a cliff, making it even more vulnerable to the partial discharge we just talked about.
So you have the electrical bombardment from the partial discharge, and simultaneously the extreme heat is baking the resins and polymers, making them brittle,
Yeah.
which sets the stage for the third major stressor, which the sources call thermal mechanical abrasion.
Right, because an EV motor isn't just hot, it's a dynamic, spinning, vibrating machine subjected to massive temperature swings.
Sure.
If you're a driver in, say, Minnesota, your car goes from sitting in negative 40-degree weather overnight to heating up to 150 degrees on a heavy highway commute. And that introduces the coefficient of thermal expansion, or CTE, mismatch.
CTE mismatch. Okay, so connecting this to the physical architecture, you have a stator core made of silicon steel, you have copper windings, and you have the impregnating resin.
Yes.
And all three of those materials expand and contract at fundamentally different rates when the temperature changes.
Exactly. And when you combine those rapid temperature swings with the high-frequency physical vibrations of the rotor spinning at, 12,000 RPM, those microscopic interfaces experience immense shear stress.
So combined with the high-frequency vibrations, these materials are basically rubbing against each other. It adds like microscopic sandpaper wearing away the enamel on the wires over time.
That's exactly what's happening. It's structural fatigue compounding the chemical and electrical degradation. And if that environment wasn't hostile enough, there is a final, highly insidious root cause, electrochemical migration, or ECM.
Oh man, this is the one that really got me in the notes because it sounds almost biological. We tend to think of motors as perfectly sealed vaults, but nothing is perfect forever.
Right, O-rings degrade.
Exactly. Moisture, road salt, or even transmission oil containing metal flakes can eventually sneak past those degraded O-rings.
And this isn't just about water causing a traditional short circuit. In the presence of a massive electric field, that external contamination acts as an electrolyte. It sets up a localized electrochemical cell inside the motor. The exposed copper acts as an anode, and the iron core acts as a cathode.
Wait, so the electric field literally starts stripping metal ions off the bare copper wire?
It does. The copper ions dissolve into the moisture, they migrate across the gap under the force of the electric field, and plate themselves onto the cathode. Over time, this literally grows microscopic metal dendrites.
Dendrites.
Yeah, they look like jagged metallic tree roots just reaching across the gap.
That is terrifying. It's physically building a conductive bridge across the void.
Yeah.
And once that dendrite touches the other side, it creates a low impedance leakage path. Your insulation resistance just vanishes.
And that brings us to the ultimate engineering challenge. You have high-frequency voltage spikes, exponential thermal decay, mechanical shear stress, and dendritic growth, all conspiring to break the insulation.
It's a war zone in there.
It really is. So the vehicle's architecture needs an immune system. How does the motor controller actually detect this microscopic damage before one of those dendrites triggers a catastrophic fault?
Right. Knowing that heat, friction, voltage spikes, and chemical reactions are constantly attacking the motor, how does the vehicle's brain actually spot this before things short circuit? If we have 60 milliseconds to react, the detection software has to be infallible.
Absolutely.
And looking at the blueprint, it's a multi-layered diagnostic strategy. Let's start with the routine checkup, which is active insulation monitoring. or IMD.
Right. The IMD operates continuously on the high-voltage DC bus. It injects a low-frequency electrical pulse into the system and calculates the isolation resistance back to the chassis.
Okay.
It's essentially probing the perimeter, asking, is any current finding a path through the motor housing into the physical frame of the car?
And there are strict thresholds here. A healthy system obviously has massive resistance. But if that isolation resistance, the RIS, dips below 100K ohms, the system triggers a level 1 warning.
Correct.
It flags that degradation is happening.
Yeah.
And if it drops below 10K ohms, that is a level 2 fatal fault.
That's a very solid way to visualize the baseline health check. But the inherent flaw with pulse injection is that it's periodic.
Exactly. A routine checkup is great, but what if a failure happens between those pulses? Like if you are doing 80 miles an hour and a brittle piece of enamel suddenly cracks wide open between diagnostic pings, you don't have time to wait. How fast can the system actually react to that?
For that lightning reflex, the system relies on transient leakage monitoring, which is fundamentally built on Kirchhoff's current law.
KCL. Okay. Let's unpack the physics of Kirchhoff's law for the listener in this specific context.
Sure. So in a balanced three-phase AC motor, Kirchhoff's law basically states that the sum of the currents going through the three phases must always equal 0.
Right.
If you measure phase A, phase B, and phase C simultaneously and add them up, they cancel each other out perfectly. I mean, in reality, there is a tiny acceptable parasitic leakage of a few microamps, but it's mathematically stable.
But if an insulation layer fails and current starts escaping to the chassis, that equation breaks. The sum of the three phases, Ia plus I, no longer equals 0. There's a remainder.
And that remainder is the transient leak, the I leak. The diagnostic algorithm monitors that sum at the microprocessor level. If it detects even a milliamp level DC or AC bias, meaning the sum shifts away from 0, it immediately registers a fault.
Wow.
And because it's purely mathematical and processed at the hardware level, this algorithm locks onto a sudden leak in just 2 milliseconds.
2 milliseconds to detect the fault. That is staggering.
It's incredibly fast.
But as fast as that is, it's still reactive, right? It's catching a leak that is already happening. The architecture uses a third diagnostic layer that is purely predictive, which is zero sequence voltage diagnostics.
Yes.
Yeah.
This is where the diagnostic software becomes incredibly elegant. This algorithm monitors the neutral point zero sequence voltage and the high-frequency common mode current of the inverter. What it is fundamentally looking for is a shift in the system's resonant frequency.
Okay, here's where it gets really interesting. It's like tapping a fine crystal glass and listening to the pitch. Even before it physically breaks, if a microfracture develops inside, the pitch changes because the microscopic structure has weakened.
That's an excellent analogy. Electrically speaking, any two conductors separated by an insulator form a capacitor.
Okay.
The copper wire and the iron core are the conductors, and the enamel is the insulator. As that enamel degrades, as it carbonizes or thins out, its dielectric constant changes.
So the parasitic capacitance of the motor actually shifts.
Exactly. And because the motor acts as an LC circuit, combining inductance and capacitance, when you change the capacitance, you shift the resonant frequency. Every time those SiC inverters fire their high-speed pulses, the algorithm is basically listening to how those electrical waves resonate. If the frequency begins to drift, the software knows the molecular structure of the insulation is failing long before a physical short circuit or a milliamp leak ever actually occurs.
It's basically a fortune teller predicting the failure based on electrical acoustics. That is brilliant.
It really is.
Okay, so the immune system has heard the crystal glass shift, or the KCL algorithm has caught a 2 millisecond mathematical leak. The system knows the insulation is compromised. The timer starts. We have less than 60 milliseconds to react. What physically happens in the car?
Well, this brings us into the fallback strategies. The system's response is highly orchestrated, and it's based on the severity of the drop in resistance. Let's tackle the mild degradation scenario first.
Okay.
If the resistance drops below 100K ohms, but hasn't breached the fatal 10K limit, the system initiates thermal and voltage derating.
Which throws the car into limp home mode.
Correct. The immediate priority is reducing electromagnetic and thermal stress to prevent a complete rupture. The motor controller intentionally lowers the bus voltage and slows down the switching frequency of the inverter.
Which directly attacks the root cause we discussed earlier. By slowing the switching, you flatten out that brutal dv/dt voltage spike, stopping the wave reflections that cause the partial discharge. Exactly.
And it caps the speed at 40 kilometers per hour, limits the torque by 30%, and basically puts the powertrain on bed rest so you can safely pull over.
Right, it contains the damage safely. But what if it's a severe breakdown? What if the KCL detects a massive transient leak and the resistance drops below 10K ohms instantly?
Yeah, if the car detects a catastrophic short in 2 milliseconds, why doesn't it just immediately pop the main contactors and sever the high voltage battery connection? Like, just pull the plug.
Because if you're going over 80 kilometers per hour, simply shutting off is arguably more dangerous than the short circuit itself.
Really?
Yeah, this comes down to a critical physics concept called back electromotive force, or back EMF. You have to remember that a traction motor is a permanent magnet machine. The physical momentum of the vehicle rolling down the highway is keeping that rotor spinning at incredibly high RPMs.
Oh, I see. So if you disconnect the battery, the motor doesn't just stop. It instantly becomes a massive high voltage generator.
Eh?
Exactly. It starts pumping out lethal amounts of uncontrolled voltage back toward the inverter. If you simply open the relays and let that massive inductive energy hit a disconnected circuit, the voltage will spike astronomically. It will blast right through whatever insulation is left, destroy the power electronics, and likely create a massive electrical arc, resulting in a fire.
So you literally cannot cut the cord. You have to safely absorb and dissipate the kinetic energy of a 2-ton vehicle moving at highway speeds purely through electrical switching in under 60 milliseconds. How do they do that?
The controller executes an emergency maneuver called a stepwise active short circuit, or ASC. Instead of opening the circuit to the battery, the inverter intentionally short-circuits specific motor phases against each other in a microsecond perfect stepwise sequence.
It deliberately shorts the motor. That sounds counterintuitive.
Yes, but in a highly controlled manner. By shorting the phases, it collapses the magnetic field. It forces the motor to swallow its own generated energy, circulating that current internally within the motor coils and the inverter switches, rather than letting the voltage spike.
Okay.
This effectively clamps the uncontrolled back EMF voltage down to a safe, manageable level, specifically keeping the system bus below 720 volts, ensuring a safe shutdown.
And once the voltage is clamped and the electromagnetic storm is contained, then it can safely open the main contactors and shut the system down.
Exactly.
That is a breathtaking sequence of events.
Hmm.
But as phenomenal as that fallback strategy is, a system is only truly safe if it never has to use it, right?
Which pivots us perfectly from diagnostics to prevention. Everything we've discussed so far is how to survive a failure. The design failure mode and effects analysis, or DFMEA, is how engineers ensure the failure never occurs in the first place.
Right, the DFMEA prevention controls. Let's look at how they armor the hardware at the design level. Because standard copper wire isn't going to survive 10 kilovolts per microsecond. The design mandate strictly requires corona-resistant wire.
Yes.
How do you physically design a wire to withstand an electron avalanche?
Well, you have to alter the chemistry of the enamel coating at the nanometer scale. Standard polymer resins eventually succumb to ozone and electron bombardment. So material scientists dope the enamel with inorganic nano-oxide fillers.
Nano-oxide fillers.
Right, these are typically microscopic ceramic-like particles like silica or alumina dispersed evenly throughout the polymer matrix.
So when the partial discharge storm starts, the polymer chains might take some damage, but the electrons quickly hit these inorganic ceramic shields. And ceramic doesn't oxidize or degrade under electrical stress the way plastic does. It acts as a physical barricade.
Precisely. It drastically increases the material's endurance. The validation metric for this wire is incredibly stringent. It must maintain a partial discharge inception voltage, a PDIV, of at least 1.5 times the maximum system bus voltage, even while continuously operating at 150 degrees Celsius.
So they demand a 50% safety margin under the absolute worst-case thermal conditions. That serious armoring. And the stator slot itself gets a multi-layer fortress too, right? Using NMN insulation paper.
Yeah, NMN stands for Nomex Mylar Nomex. When they insert the coiled wires into the grounded iron core, they don't rely solely on the wire enamel. They line the slots with this 3-layer composite.
Okay.
The Mylar in the center provides exceptional dielectric strength to block current leakage, while the outer layers of Nomex, which is the same aramid fiber used in firefighter gear, provide thermal stability and mechanical protection against vibration.
Oh, wow. Firefighter gear in the motor. But even with nanotech wires and Nomex fortresses, you are still letting that brutal series voltage spike hit the motor. The root cause is still there. Remember that brutal 10 kV per microsecond voltage slap from the SIP to P inverter? If we can't change the inverter because we need the efficiency, how do we protect the motor?
By physically altering the shape of the electrical wave before it arrives. Engineers implement an optimized high-frequency LC filter, or a common mode magnetic ring, at the inverter output.
Okay, let's break down the LC filter physics. That's an inductor, L, and a capacitor, C. How do they reshape the wave?
It comes down to basic electromagnetism. An inductor inherently resists any sudden change in current, while a capacitor inherently resists any sudden change in voltage.
Right.
When the SIT inverter fires a massive square-wave voltage spike at 10 kilovolts per microsecond, it hits that LC filter.
And the inductor slows the current surge while the capacitor absorbs and smooths the voltage edge.
Exactly. They act as electromagnetic shock absorbers. By the time that wave reaches the motor terminals, the filter has squashed the violent vertical spike into a gentle slope, bringing the dVdt stress down from 10 kilovolts per microsecond to under 1.5 kilovolts per microsecond.
It is like putting a massive shock absorber between a sledgehammer and a piece of glass. You basically eliminate the wave reflection and the impedance mismatch at the motor.
You do?
The overstress condition required to trigger partial discharge just ceases to exist. That is deeply satisfying engineering.
It really is.
But here's the vulnerability. A perfect design on a computer screen is useless if it is put together poorly on the assembly line. You can design the most resilient nanotech LC filtered motor in the world, but if a robotic arm pulls a wire a fraction of a millimeter too tight on the line, you've introduced a fatal flaw.
Which is why the process failure mode and effects analysis, the PFMEA, is arguably more critical than the design itself. The manufacturing process controls must be flawless to maintain the integrity of those microscopic nanofillers.
So how do they manufacture this without scratching a single microscopic wire? Let's talk about the precision winding. You can't just forcefully yank copper off a spool into a stator.
No, definitely not.
The assembly relies on needle winding technology with closed-loop tension control, accurate to plus or minus 1 Newton. Why is that specific tolerance so critical?
Because if the tension fluctuates, or if a wire drags across the edge of the stator slot with too much force, it inflicts a micro-scratch on the enamel. We were talking about abrasions thinner than a human hair.
But electrically, a scratch is a disaster.
Completely. A scratch reduces the thickness of the dielectric. In electromagnetics, electric fields concentrate at sharp edges and thin points.
Oh, right.
That microscopic scratch becomes a focal point for intense electrical stress. The partial discharge will initiate exactly at that scratch, basically boring into the wire like a laser. The plus or minus 1 Newton tension control guarantees absolute physical perfection, 0 microscratches during winding.
Okay, so the coils are wound flawlessly, and now they have to be locked into place and insulated further using vacuum pressure impregnation, or VPI. So what does this all mean for the resin? It sounds like they are basically forcing honey into a sponge, right?
That's a good visual, yeah.
Yeah.
Exactly. You aren't just dipping the motor in a vat of epoxy. Air is the enemy here. Any microscopic void left between the wires will eventually ionize and cause partial discharge. So the VPI process manipulates atmospheric pressure to eradicate the air entirely.
So they put the entire assembled stator into a chamber and pull a massive vacuum, bringing the pressure down to roughly 10 millibars.
Yes. They hold that vacuum until every single molecule of trapped air is violently sucked out from deep within the dense copper windings. Once the motor is entirely evacuated, they flood the chamber with the specialized impregnating resin.
But they don't stop there. Once it is flooded, they reverse the process and blast the chamber with 6 bar of positive pressure to force the resin in.
Right. That intense pressure mechanically forces the resin into the microscopic intermolecular spaces between the wires. It fills every single void where an air bubble used to be. And the verification is just as intense. After curing, they run the stators through industrial 3D CT scans. They're looking for 100% material density. 0 air pockets means 0 room for partial discharges to occur.
It's an obsessive level of quality control, and that obsession continues to the end of the line. Before a motor is ever cleared for shipping, it goes through an interrogation process. Now, standard factory testing usually involves a high pot test, basically blasting it with high voltage to see if it immediately shorts out.
Yeah.
But a high pot test is too blunt to catch a micro scratch, right?
Yeah, a standard high pot test is completely blind to early stage degradation. That's why advanced lines use 100% online partial discharge testing. They inject a highly calibrated 2.5 kilovolt surge, specifically designed to catch weak discharges that standard tests miss.
We are talking about detecting discharges at the scale of less than 10 picocoulombs.
Right. A picocoulomb is 1/1,000,000th of a coulomb of electrical charge. It is almost imperceptible. If even a single microscopic manufacturing defect made it past the needle winding and the VPI process, the surge test will illuminate that 10 picocoulomb leak and the unit is scrapped.
And they applied that same rigorous standard to the mechanical seals. To prevent that terrifying electrochemical dendritic growth we discussed earlier, the FKM O-rings are servo-assembled and immediately subjected to a dual-stage helium leak test.
Helium is used because it's an incredibly tiny noble gas molecule.
Yeah.
If helium can't escape the sealed housing, you can be absolutely certain that much larger moisture or transmission oil molecules cannot get in.
Right.
They mandate a maximum leak rate of 1 × 10⁵ millibar liters per second. No moisture gets in, period.
So the system is environmentally impenetrable. The design is locked. The manufacturing is flawless and validated by CT scans and helium. But engineers are natural skeptics. Now they have to prove that this pristine system works by putting the motors through absolute hell.
Oh yeah. That brings us to the ultimate torture test, the DVP&R, or Design Verification Plan and Report. This is where they intentionally try to destroy their own creation through accelerated life testing.
Let's start with the VDA 320 LV124 gauntlet. If you want to talk about condensing a lifetime of abuse into a few weeks, this is it.
This is a combined environmental, mechanical, and electrical endurance test. They mount the fully assembled motor onto a vibration table inside an environmental chamber. They subject it to violent thermal shocks, plunging the temperature from -40 °C up to a baking 150 degrees.
And while the thermal expansion and contraction are torturing the silicon steel and copper, they hit it with 3-axis random vibration at 35 meters per second squared.
Creating immense shear stress. But the real kicker is that while it is freezing, baking, and shaking, they continuously run that brutal 10 kilovolt per microsecond electrical switching for over 1,000 hours.
Over 40 straight days of absolute hell, and the result must be zero cracking or carbonization on the wire enamel. The insulation has to measure as pristine as the day it was manufactured.
It proves the nanotech and the LC filters work. But what about the seals? For that, they execute the IP69K flood test.
Oh, this one is brutal.
It is. They start by aging the motor, running it through 100 cycles at 85 degrees Celsius and 85% relative humidity, just trying to degrade the rubber O-rings. Then they hit it with 96 straight hours of highly corrosive salt spray.
And then comes the IP69K designation, which literally means blasting the motor interfaces and seals with a high-temperature, high-pressure industrial water jet.
Right.
After all of that chemical and physical abuse, they apply a 500-volt DC megger test for 60 seconds. The resistance must stay above 100 megaohms with 0 drop of fluid inside, not a microliter of moisture.
Exactly. The hardware is basically indestructible.
But what about the software? How do you validate that the KCL Diagnostics and the stepwise ASC can actually catch a fault and save the car in 60 milliseconds?
That requires the hardware-in-the-loop, or HIL dynamometer test. It is essentially an orchestrated assassination attempt on the motor controller.
So they run the motor at 12,000 RPM on a dynamometer and then literally hack it, injecting a sudden 5K ohm fault to see if the brain can catch it.
Yeah, they mathematically simulate a catastrophic insulation rupture, the ultimate test of the 60 millisecond FTTI rule.
The timer starts. 0 milliseconds.
The controller's KCL algorithm must detect the transient leakage in 2 milliseconds. They have to calculate the vehicle's speed, realize that opening the contactors will cause a lethal back EMF spike, and calculate the firing sequence to initiate the stepwise ASC.
Right.
It triggers the inverter switches, shorting the coils, collapsing the magnetic field, and clamping the generated voltage below 720 volts. And finally, it safely transitions the vehicle into limp home mode.
And every single step of that complex sequence must be completed before the stopwatch hits 60 milliseconds. If it takes 61, it fails.
Exactly. It is the ultimate proof that the hardware and software are operating in perfect, life-saving symphony.
It adds a staggering amount of invisible engineering dedicated entirely to making sure that the driver simply hears a chime and safely pulls over, completely unaware of the electromagnetic violence that was just contained. It totally changes how you view a simple drive down the highway.
It really does.
So we've wrapped up this massive journey from the physics of high-frequency electron bombardment down to the factory floor's helium leak tests, emphasizing how invisible engineering keeps drivers incredibly safe. But before we sign off, there is an incredible piece of forward-looking research in the source notes that we need to touch on.
Ah, yes, the Python data tools.
Yes, this is a fascinating final nugget. What if, using high-voltage, zero-sequence voltage features and high-frequency common-mode current spectrum waveforms, we could build resonance shift models?
This is where the predictive capabilities are heading next. By porting those features into Python-based data environments, we can build vastly more complex resonance shift models. This provides a completely non-intrusive early warning algorithm.
So instead of just reacting to failures in 60 milliseconds, what if future EVs use these Python-modeled spectrums to essentially feel their own insulation dying months in advance?
They can track the degradation curve for months, predicting exactly when a failure would occur.
And then calmly schedule their own maintenance appointment before a single dendrite or partial discharge ever puts the driver in danger. It has the ultimate evolution from reactive safety to true predictive immunity, something for everyone to ponder.
It is a profound shift in how we approach machine mortality.
Absolutely. Well, a great place to leave it.